This is 1979 IMO problem number 3, and here is a view of this problem. It's a geometry problem. We're given two circles which intersect at the point A, and let's call the other one B probably, at the points A and B. Then at point A, two particles start moving in the same, let's say, counterclockwise orientation. But the idea is that after the 2 points return to point A at the same, the two particles, they return to point A right after one revolution, so meaning that they have the same speed, right? When I say speed, obviously because one of the circles is bigger, larger, this is omega 1 is a bigger circle than omega 2. Particle 1 is faster than particle 2 in terms of its velocity speed, but in terms of angular speed, if you will, right? So they trace the speed of rate of change of the angle, central angle here. Let's call this angle theta, right? So they go in the same in same speed. So for instance, after a certain time, if particle 1 is at point q1, particle 2 would be at point where such that AO1 Q1 is equal to AO2 Q2, right? So at each time, so at time t, let's write that at time t, then we have angle AO1 Q1 is equal to AO2 Q2. So at time t, we have particle 1 at particle 1 at q1 and similarly particle 2 at q2, such that this holds. Okay, then the question is asking for this stuff. So apparently there exists such a point P, a fixed point, such that the 2 points, in this case q1 and q2 at time t, obviously q1 and q2 will change, but q1 and q2 are equidistant to, well, it's easy to find that, right? It's just you would draw the perpendicular bisector, and I don't want to mess up my picture, but so a point on that perpendicular bisector joining the line q1 q2 is apparently a candidate, right? So but where exactly on that perpendicular bisector? So first let's try to establish the line segment q1 q2, and it seems like q1 q2 goes through point B, right? So let's start from that. So let's go ahead and connect AB, which is part of the radical axis, and let's measure angle ABQ1. It's clear that ABQ1 is half of angle theta here. So that's just theta over 2. And in a similar way, let's connect BQ2. Right now, I don't know if Q1, BQ2 are collinear, but I know exactly how much this angle measures, right? It measures because ABQ2... no, they are not cyclic. I was about to say that ABQ2O2 is cyclic. No. Okay, so how about that? So this whole angle is 360 minus theta. It subtends this major arc AQ2, so therefore that arc is also subtended by angle ABQ2, so therefore this would be half of that angle, which is 180 minus theta over 2. Hey, look at that. So angle Q1, sorry for that, Q1 BA plus angle Q2 B, oh my god, I don't know how to write the letter B, huh? So Q2BA, that's equal to what? Oh, okay, let's write it like this. That's just equal to, the first angle is just theta over 2, plus the second one is 180 minus theta over 2. We just established that, 180. These two angles, they are supplementary angles, and as such it implies, so this implies that Q1, B, and Q2 are collinear points. Awesome. So we now know that Q1, Q2 goes through the point B. That's crucial, right? So from now on, if I want to see, for instance, if I wonder where the particle, if the first particle is, say, at this point, and I wonder Q1 prime, and I wonder where the second particle is at that time. I don't need to measure angles any longer. All I do is I connect this point through B and I let it intersect here, and boom, and I have the Q2 prime, the second particle, the location of the second particle. Actually, at this stage, you might say, hey, now I can find it. Well, now I can draw the perpendicular bisector of Q1, Q2. I don't know, maybe, is that where the midpoint is? So probably no, it's probably somewhere here. We can more or less draw the perpendicular bisector now here, and I can try something similar. Something similar here. I can try to draw the perpendicular. So we have kind of a guess. It will be somewhere. So the intersection is probably somewhere around here. But anyhow, okay. This is just speculation, obviously. We can't know it for sure until, so this is 90 degrees, until we are really done with our thing. But how to proceed? Look at this perpendicular bisector. It gives me an idea of drawing parallel lines. So if this is the perpendicular bisector of Q1, Q2, I can go ahead and draw a line parallel to that bisector. Say, so because it's parallel, this angle would be obviously 90 degrees. So something like this. Look at this point here. Let me call it R. And I'll do the same thing from this point Q2. I'll draw a perpendicular. Like that, I guess. Okay, and let's call this one as S now. Oh, that's not 90 degrees. Okay. Let's just fix our picture here. 90 is more like this. There you go. Okay, boom. All right. So that's the point S. That's the circle omega 2. All right. So what's going on? So hey, the perpendicular. Wait a second. First, let's look at R and S. Seems like RAS are collinear. Are they really? Let's test it. First of all, because we have a 90-degree angle here, this is RB is a diameter, but we know because the diameter will go through the center of that circle. So RO1B is a diameter. Similarly, we have a 90-degree. Oh, my picture is pretty messed up here, actually. Yeah. So similarly, we have, this is 90 degrees, suggesting that SQ2B is also a diameter. There you go. So RB is a diameter. Let's write that. RB and SB diameters. Oops, SB diameters. Okay, but what? Oh, look at this. So RB is subtended by angle RAB. So that's 90 for sure because it subtends diameter. And look at this. SAB also subtends the diameter. Boom, 90 degrees. Hey, RAS are collinear. So therefore, let's just do it over here. So angle RAB equals 90 degrees, which is also angle SAB, implying that RAS also collinear. Now we have what we need, right? So now you have a trapezoid. Q1, Q2, SR is a trapezoid. Q1, Q2, SR, trapezoid. And look at what I have here. I know that, so if you call this point a midpoint M, let's call it M. So Q1M is equal to Q2M because you have this perpendicular bisector here, a 90-degree angle. It is like a midline, right? So it hits this at the point, say, call it P. So trapezoid and MP is midline. When I say midline, what I mean is Q1R is parallel to MP, which is parallel to Q2S. And now I'm done because I claim that that point P is this desired point that I'm looking for. Why is that? Because AB, which is the radical axis. So once you are given two circles, so the circles are fixed. Omega 1 and omega 2 are fixed. Then the radical axis AB is fixed. Once AB is fixed, I can draw a line. So I can go. So now I'm going backwards, right? I can draw this line RS easily because all I do is I just draw a line perpendicular to AB, and therefore I can locate R and S easily. Once R and S are easily located, once you have Q1, Q2 for one point, because RS is fixed, the perpendicular bisector, it hits this midpoint here, but the same thing will happen for the other, so because it's independent of the choice of Q1, Q2, right? The same thing will happen for other choices of points. For instance, let's draw it with a different color here. If I did the same trick, I did go ahead and complete it in, so this one would be also, if I draw a perpendicular here, it would have to go through R again, right? The same thing will happen here. And when I draw the perpendicular bisector, like I tried to do earlier, it will of course have to go through the point P, because if you call this point N, NP is a midline of trapezoid, say Q2 prime, Q1 prime, RS, right? Does that make sense? So therefore, it must be the case that the midpoint of RS is this desired point, and I have shown how to construct RS, right? All you do is you have the radical axis AB, and you draw a perpendicular to AB at the point A. It hits the circles at point R and S, and boom, you calculate the midpoint of line segment RS, call it P, and that's the midpoint. And that point P is the desired point. So P is equidistant, right? So for instance, just to give you an idea on which color to use, I don't know, blue. Okay, blue. So the distance Q1P, of course, would be equal to Q2P, right? It's clear because MP is the perpendicular bisector of Q1, Q2. Similarly, for example, you can easily, Q1P is, Q1 prime P has the same length as Q2 prime P as well. So that point P is the magical point, basically, that satisfies the conditions of the problem. So that solves this problem. Hope you enjoyed it, and looking forward to see you guys in our next lecture.